Welcome to Chapter 7, Detecting and Correcting Errors. Digital does not mean perfect. Out in the real world, noise and radiation and wear can flip a single bit, and one flipped bit can corrupt everything. So we fight back. We add extra bits on purpose so a message can catch and sometimes even repair its own damage. In this chapter, you will learn parity, Hamming codes, and CRC. Digital does not mean perfect. Every wire, every radio link, every memory chip, and every disk works in a physical world. Noise, radiation, and wear can flip a bit. A 0 becomes a 1, or a 1 becomes a 0. And one flip bit can corrupt your data. In 2003, a voting machine in Belgium gave a candidate 4,096 extra votes, all from a single flipped bit in memory. This chapter is about fighting back. We add extra bits on purpose, so a message can catch its own errors and sometimes even repair them. Let's look at the plan for this video. It has 3 parts. First, parity, one extra bit that catches a single flip. Second, Hamming codes, the centerpiece. They do not just detect an error, they find which single bit is wrong and correct it using the syndrome. And third, CRC and Checksums, strong ways to detect errors that networks and storage rely on every day. Let's start with the cheapest defense there is. It costs exactly 1 bit. Before you send a byte, you count its 1 bits. Take the data byte 10110010. Count the ones. There are 4, an even number. Even parity means the total number of ones. The data bits plus the parity bit must be even. The data already has 4, so the parity bit is 0. You send 9 bits, and the total number of ones is still 4, which is even. That even count is the promise the receiver will check. Now the message travels and noise flips 1 bit. A 0 becomes a 1. Look at the received bits. They now hold 5 ones, an odd number. Even parity promised an even count, but 5 is odd. The promise is broken, so the parity check fails, and the receiver knows an error happened. 1 extra bit caught the mistake. Parity is honest about its limits. It tells you that an error happened, but not where. It cannot say which bit is wrong, so it cannot fix it. And if 2 bits flip, the number of ones changes by an even amount, maybe even 0, so parity sees nothing. Parity misses any even number of flips. It catches a single flip cheaply. For real protection, we need something smarter. In 1950, Richard Hamming built a code that does more than detect an error. When a single bit is wrong, it points to the exact bit and corrects it. A Hamming 7-4 code is a code word of 7 bits, 4 data bits and 3 parity bits. The parity bits sit at the power of 2 positions. Parity 1 is at position 1. Parity 2 is at position 2. Parity 4 is at position 4. The data bits fill the rest, positions 3, 5, 6, and 7. We name each parity bit after its position. Each parity bit watches a different set of positions. Parity 1 checks positions 1, 3, 5, and 7. Parity 2 checks positions 2, 3, 6, and 7. Parity 4 checks positions 4, 5, 6, and 7. The rule is neat. Write each position number in binary, and a parity watches it when the matching bit is set. That overlap is what lets the code pinpoint an error later. Let's encode the data 1011, 1 parity at a time. The data bits fill positions 3, 5, 6, and 7. Parity 1 covers positions 1, 3, 5, and 7, so we XOR the data at 3, 5, and 7. 1 XOR 0, XOR 1 is 0, so parity 1 is 0. Parity 2 covers 2, 3, 6, and 7, so we XOR the data at 3, 6, and 7. 1 XOR 1 XOR 1 is 1. Parity 2 is 1. Parity 4 covers 4, 5, 6, and 7, so we XOR the data at 5, 6, and 7. 0 XOR 1 XOR 1 is 0. Parity 4 is 0. Slot them in and read positions 1 through 7. The code word is 0110011. There it is. The data 1011 became the 7-bit code word 0110011. 3 parity bits at positions 1, 2, and 4 now protect the 4 data bits, and we are ready to send it across a noisy channel. The code word leaves the sender. On the way noise flips position 5, its 0 becomes a 1. The receiver sees 0110111. One bit is wrong, and its job is to find which one, using only the parity rules. The receiver rechecks each parity group with XOR check parity 1 over positions 1, 3, 5, and 7. 0 XOR 1 XOR 1 XOR 1 is 1. That fails, so the first syndrome bit is 1. Check parity 2 over positions 2, 3, 6, and 7. 1 XOR 1 XOR 1 XOR 1 is 0. That passes, so the second syndrome bit is 0. Check parity 4 over positions 4, 5, 6, and 7. 0 XOR 1 XOR 1 XOR 1 is 1. That fails, so the third syndrome bit is 1. Read the 3 results as a binary number S4, S2, S1, 101. That is the syndrome, and 101 in binary is 5. The 3 checks read S4, S2, S1, which is 101. In binary, 101 is 5. This number is called the syndrome, and it is not just a yes or no. It is the exact position of the wrong bit, position 5. So flip position 5 back, and the code word is repaired to 0110011. The error is not just detected, it is corrected. So what can a Hamming code do, and what can it not do? A Hamming 7-4 code corrects any single bit error. Find it, flip it, done. Its minimum distance is 3, which means it can correct 1 error, or instead detect 2. But 2 flips fool it. The syndrome then points at the wrong bit. Adding 1 more overall parity bit, a scheme called single error correction, double error detection, lets it catch 2 errors as well. This is what the ECC memory in your computer uses, silently all day. Parity and Hamming work bit by bit. CRC takes a whole block and gives it a powerful check value using division. CRC treats a bit string as a polynomial and divides it. Each bit is a coefficient, and you never really compute powers. The polynomial is just another way to write the bits. All the arithmetic is modulo 2, and in modulo 2, adding and subtracting are the same operation, XOR. 1 XOR 1 is 0, with no carry. That no carry rule is what makes the division simple enough for hardware. This is the plan for a CRC take the message 110101, 6 data bits. Pick a generator, 1011 of degree 3. Degree 3 means a 3-bit check value. Append 3 0 bits to the message, giving 110101,000. Those zeros make room for the remainder we are about to compute. Now divide by XOR, one step at a time, like long division without carries. Take the first 4 bits, 1101, and XOR the generator 1011. That gives 0110. Bring down the next bit in XOR again. 1100 XOR 1011 is 0111. Bring down a 1 in XOR. 1111 XOR 1011 is 0100. Bring down a 0 in XOR. 1000 XOR 1011 is 0011. Bring down the next bit. A leading 0 just skips, then XOR the last window. 1100 XOR 1011 is 0111. The last 3 bits are the remainder, 111. That is the CRC. The remainder 111 is the CRC. The sender transmits the message followed by the check value, 110101, then 111. The receiver divides the whole block by the same generator, 1011. If the data is clean, the remainder is 000, and the block is accepted. Any flipped bit almost always makes the remainder non-zero, and the error is caught. So what does CRC give you, and what does it not? CRC is strong detection, but it does not correct. It cannot fix a bit. It tells you the block is bad, so you ask for it again. A generator of degree R catches every burst error up to R bits long, guaranteed. That is why CRC32 guards every Ethernet frame, every zip archive, and every PNG image. Checksums are simpler and weaker. Just add up the bytes and send the sum. Good enough for many jobs. And to correct errors, not just detect them, you reach for a code like Hamming. Let us gather what this chapter gave you. 4 takeaways. First, errors are physical. Noise, cosmic rays, and scratches flip bits, and we fight back by adding redundancy on purpose. Second, a parity bit catches a single flip, but it cannot locate the bit, and it misses any even number of flips. Third, a Hamming 7-4 code places parity bits at positions 1, 2, and 4. The syndrome names the wrong bit, so the code corrects one error. The data 1011 became the code word 0, 110011. Fourth, CRC divides the message by a generator using XOR, and the remainder is a check value that detects burst errors, widely used in Ethernet, ZIP, and PNG. That is Chapter 7. You can now add a parity bit by hand, encode and decode a Hamming code word, and use its syndrome to correct a flipped bit, and compute a CRC by XOR division. This chapter added redundancy to survive noise. Chapter 8 asks a deeper question. How much information does a message actually carry? Information theory ties compression and error correction together and sets the true limits of communication. See you there.